Hello and welcome to lecture number 24 of the course User Centric Computing for Human Computer Interaction. So, before we start today's lecture, first let me briefly recollect what we have learned in the previous lecture. In the previous lecture, we started our discussion on formal models, particularly in the context of user centric systems. So, there we got introduced to some basic ideas, that is what is formalism and what is a formal model and how it is different in the context of user centric system. Also, we have briefly seen the use of the formal models, particularly in the context of verification of properties. Now, these properties are supposed to be indirectly related to the usability of the system. So, essentially by verifying these properties, by ensuring that the system supports these properties, we can ensure that the proposed system or the system that we propose to design is usable. Now, in this lecture, we are going to understand or learn about these formal models of interactive systems in more details. There are many ways in which we can think of a system. One very intuitive way to view user centric system is to think of it as a dialogue between a computer and a human user. So, essentially the system communicates with the user through the interface. So, the interface is the medium of communication for the system. Based on the interface state, whatever is the state of the interface, the user performs some interactions, essentially touch, click or such interactions, and as a result the state of the interface changes and this process continues or the dialogue continues. So, there is an interface through which the system communicates something to the user perceives that by perceiving the state of the interface. Based on that perception, the user performs some action on the interface which leads to change in the state of the interface, and that is the dialogue, and it continues till the user achieves the desired objective or achieves the goal. Then we can see that in this view of the system as a dialogue, there are two components, the interface and the interaction. By interface we mean the state of the interface, and the second component is the interaction. So, in a nutshell, what happens is that user perceives the state of the interface as the system state. Note the emphasis on the term the. So, whatever is the state of the interface is perceived by the user as the state of the whole system. So, user is not bothered about the internal working, how the memory content looks, how the processor is working, how the battery is consumed, or what is the bus utilization, bandwidth utilization, all these things. The user is only concerned about what he or she can perceive on the interface, and that is the state of the system for the user. And user interaction leads to state transition. So, essentially by interacting with the interface, the user can take the system to a new state. These are the basic components of a view of the system, where we think of the system as a dialogue between the user and the computer. So, if that is the case, then we can consider modeling of the system or modeling of the interactive system as dialogue modeling as well. So, when we say that we want to model our interactive system in terms of system states and transition between states, essentially what we are trying to model? We are trying to model the dialogue between the system and the user. So, system modeling is equivalent to modeling the dialogue as well. In other words, we consider the dialogue to be the system. So, earlier we considered the system to be a composition of system, state and transition. Now, we are saying that this is nothing but the dialogue between the user and the computer, and our objective is to formally model this dialogue. Now, earlier in the previous lecture, we have seen that state transition networks can be used to model the system. We can use states and transitions between them, use the state transition network notation to model the system of states and transitions. However, all our examples were for simple systems. So, if the system becomes too complex, then the basic state transition networks that we have seen in the examples in the previous lecture will not be sufficient to model such complex systems, and we require some better modeling techniques. In this lecture, we are going to discuss about few of some advanced modeling languages for modeling complex interactive systems. Let us reconsider the example system that we have introduced in our last lecture, the character display system. Recollect that it is only a simple system. It has only a very simple interface which is capable of showing only one letter of the English alphabet, one letter in capital, and we can change the font size of this letter and we can change the color of this letter. So, there are 26 capital letters in the English alphabet. We can change its font size by making it one of the 8 possible values that we have defined as mentioned in the earlier lecture, and also we can change its color between red and black. So, total we have identified 416 states for this simple interface system, and between these states there will be transitions. So, the total number of transitions will be large. Now, we want to basically represent this system in the form of STNs. So, for that we need to probably draw it on paper, but as we have already mentioned, drawing such a large number of states and transitions on a paper for visual inspection and analysis is too complex a task. You may argue that it is not necessary to always draw STNs. Instead, what we can do is that we can use some programming language construct to specify the STNs and then perform some analysis on this specification. But that itself is not easy. Unless we are able to visualize the whole system, we are likely to make some mistakes during specification as well. For example, we may miss some states or some connecting arcs between states during specification because we are unable to visualize it. Now, what is the consequence of such mistakes? There can be many consequences. Actually, by making those mistakes, we can violate various desirable system properties which otherwise would have been there. For example, by making the mistake, we can actually develop a STN which may lack completeness, or sometimes we may end up with a model that has a reachability issue. Other properties may also get violated. Then that defeats the whole purpose. So, we have actually designed something very nice which supports certain properties which ensures usability indirectly. However, during specification for letter analysis or during coding of that model for software development which involves specification, we may end up specifying the model wrongly, which may lead to violation of certain properties. So, our design is okay, but our specification is the problem. Now, why this problem happened? Primarily because we are unable to visualize large and complex systems. And how we can resolve this issue? We can resolve it by using a proper specification language to tackle complex system visualization. In fact, most of the practical systems are large and complex. They are not simple systems that we have encountered in our examples, and unless we are able to properly visualize those systems, it is difficult to encode or specify those systems in computer. So, what we need is a proper specification language, and in this lecture we are going to learn about a couple of such languages. So, we will start with one language which is called hierarchical STN or hierarchical state transition networks. The basic idea is that we can think of the whole system as a hierarchy of subsystems, and the overall model is a hierarchy of sub-dialog models with higher level connections in between. So, essentially we are thinking of the whole system not as a single system, but as a hierarchy of less complex subsystems, and we provide higher level connections to those subsystems to model the whole system. Now, if we want to use this hierarchical STN to model our example system, that is the character display system, it will look something like this figure, where we have sub-dialog models. Say one sub-dialog model may be for letters, one sub-dialog model may be for font size, and one sub-dialog model for font color. Now, between these models we have connections. So, let us have a start state. So, from start state, if we press the up or down arrow key, then we go to the sub-dialog for font size. If we press the left or right arrow key, then we go to sub-dialog for letter. From sub-dialog for letter, if we press up down arrow key, then we can come to the sub-dialog for font size, and at this sub-dialog or at this state of the system, if we press left right arrow key, then we can go to the letter sub-dialog again. Similarly, if we press space key when we are in the sub-dialog for font size state, then we can come to sub-dialog for font color, and by pressing up and down arrow key, we can go to sub-dialog for font size again. We can come to sub-dialog for font color from sub-dialog for letter by pressing the space key, and by pressing the left right arrow key, we can go to the letter sub-dialog from the color sub-dialog. And from the start state, if we press the space key, we can come to the font color sub-dialog. Now, this is a much nicer way to represent the whole system. As you can see, we managed to depict the entire system within a small area by assuming that there are sub-dialogues and there is higher level connection between those dialogues. So, each sub-dialog can be a state transition network in itself, or can be another hierarchy of state transition networks. For example, the sub-dialog for font color can be represented as a state transition network as shown in this figure, where there are two states, color equal to red and color equal to black, and with interaction by pressing the space key, we can move between these two states. Similarly, we can draw sub-dialog models for the letter and the font size as well. Now, if we are trying to do that, it may be noted that for letter sub-dialog, there are 26 states. Each state corresponds to one of the alphabetic letters, and in between them there will be 52 transitions or arcs. For font size model, since there are 8 font sizes to choose from, we can have 8 states and 16 arcs. These are still manageable compared to 416 states and arcs in between. So, what we have essentially done? We have divided the problem into sub problems. So, our entire problem was to draw the STN for the entire system. Now, we have divided it into sub problems, that is to draw STNs for specific sub dialogues, and then we have connected these sub dialogues with fewer arcs. Those are higher level arcs or transitions. Now, when we say that we reduce the complexity of the problem by dividing it into sub problems, what it means? It means that we have defined states that are having reduced number of variables, hence they have become manageable. For example, the sub dialog for font color has only one state variable, which is color. Unlike in the previous case where we were trying to model the whole system with a single STN, where we have defined 3 state variables for each state, which led to 416 combinations. Now, if we have only one variable which can take only 2 values, then there are only 2 states. So, we will be able to manage this sub dialog model in a much less space. Now, in this example, we have solved our problem with only 2 levels in the hierarchy. However, in practice, the systems are much more complex than the example system, as I am repeatedly saying, and there 2 levels may not be sufficient, and you probably have to go for many more levels and many more sub dialogues. Can we do any better? So, whatever we have seen with the hierarchical STN, it is sufficient for giving us a nice and clean model of our example system. But is there any issue with this model? Actually, there are few issues. Hierarchical STN, although formal, but still there is some ambiguity. For example, when we say that we have sub dialogues and there are higher level connections, each sub dialogue is essentially STNs in itself. Now, when we enter a state transition network, we are supposed to enter at a specific state. In the hierarchical STN notation, we have no way to actually inform which state should be entered first when the whole sub dialogue is entered for the first time, or at any instant of interaction when a sub dialogue is entered, which state to be entered, which state of that particular sub dialogue to be entered. The hierarchical STN language does not support that level of specification. The language also is not good at modeling concurrent behavior. For example, if we want to change the font size and color together, it is not clear how to represent that behavior with the notion of a hierarchical STN. There are few more issues. These 2 are among the major issues, namely ambiguity and lack of support for concurrency. Now, we can go for better formalism than the hierarchical state transition network, which is called state chart. So, we will have a brief look at the idea of state chart and how it can be used to model dialogues for interactive systems. So, what is a state chart? It is kind of visual formalism to represent complex systems, and it extends conventional state transition diagrams or STNs with essentially 3 elements dealing with hierarchy, concurrency and communication. However, we will not cover all the things in the state chart, we will only cover how it deals with hierarchy and concurrency mostly. So, state charts are nothing but state transition networks in a modified form, and they are capable of representing hierarchy and concurrency together. That is the main advantage of having a state chart notation over hierarchical state transition networks. Now, state chart notation or state chart formalism actually contains many useful elements, but we will focus on few of them which are very fundamental, namely superstate, basic state, default state mechanism, history mechanism and superstate. So, let us see one by one what these concepts mean. So, state chart, as we mentioned, is extension of state transition networks. So, it consists of states and transitions. What these states represent? There are two types of states. There are some states that are composed of other states, and these are called superstates. There are some states which are not composed of any other state. These are called basic states. For each basic state, there is a superstate, and this superstate is also known as ancestor state. So, to recap, there are two types of states. Some are composed of other states, those are called the superstates. Some are not composed of other states, those are called basic states, and for each basic state there is always a superstate. This superstate is sometimes called the ancestor state of that particular basic state. The idea is illustrated in this diagram. Here, as you can see, this is the typical convention used to represent superstate, basic state and transitions. So, B1 and B2 are the basic states, and we can define transitions between them as shown here, T1 and T2. The state that contains these two states B1 and B2 is the superstate, which we can label with a name. Here the label S is given to this superstate. Now, this superstate S is the ancestor state for both B1 and B2. So, S is a superstate which is also ancestor state for B1 and B2. B1 and B2 are the basic states. Now, state transition networks are meant for transitioning from one state to another, which is called state traversal. During the state traversal in a state chart formalism, the current state being accessed, either a basic state or a superstate, is called active state. Now, if a superstate contains only one active basic state at a time, whenever it is active, it is called OR superstate. To indicate the active basic state whenever a superstate is entered, there is a notation which is called default state mechanism, which is used to indicate the behavior. Now, this notation comprises of a filled circle with an arrow pointing to the basic state that should be active. Let us try to understand it with an illustration. So, in this figure, the concepts are highlighted. Now, this filled circle with arrow, which is shown within this red dotted circle, is the default state mechanism that we have just mentioned. So, whenever the superstate S is active in the overall state chart, then the default state mechanism indicates that B2 should become active. One important aspect of a state chart is that the way it represents entry and exit from superstate. So, default mechanism we have already talked about. There is another convention used, that is we typically draw an arc from the boundary of the superstate to indicate exit rather than drawing it from one of the basic states. So, when we want to indicate exit from the superstate, we do not directly draw an arrow or an arc from a particular basic state to outside of the superstate. Instead, from the boundary of the superstate, we draw the arc. The idea is illustrated in these figures. So, in the left side, what we have is what exactly we want, that is we have a superstate S, two basic states. Now, from B2 we want to go to B3 and from B3 we want to go to B1. So, how to denote this using state chart notation, that is shown in the right hand figure. Here, as you can see, the arcs are not directly drawn from B3 to B1 and B2 to B3, unlike in the left figure. Here from B3 the arcs are extended up to the boundary of the superstate, the arcs T3 and T4. Inside the superstate we have mentioned this default mechanism, that is whenever the superstate is entered, B1 should get active. So, it is essentially same as telling that from B3 if we enter this superstate we will go to B1. So, in this way we can indicate how to specify the entry and exit to a superstate. There is another useful notation, that is called history mechanism, which essentially indicates a memory of the superstate, that is the basic state or the active basic state before the superstate is exited. So, last time what was the active basic state before we exited the superstate. Now, why this memory is important? It ensures that next time the superstate is entered, the same basic state is activated again. So, we do not need to start from the beginning or the default state. Default state mechanism and the history mechanism can be used in tandem. So, we can use them together to indicate the behavior at the start of the state traversal and in the middle of state traversal. So, at the beginning we can apply default state mechanism, and at any instant during the state traversal we can rely on the history mechanism. The idea is illustrated in this figure, where we are combining the default mechanism with the history mechanism. So, H within this circle indicates history and the default mechanism we have already seen. So, in this superstate both the mechanisms are specified. That means, when the superstate S is entered for the first time, it starts with the default mechanism. So, it starts with B1. If it exits, then it remembers from where it exited and it starts from that state next time it is entered. So, with this notation, let us now try to see how we can build a state chart for our example system. So, remember that in our example system we have 416 states. Now, earlier we have seen how to use the hierarchical STN to divide the whole system into subsystems and come up with a hierarchical specification of the whole system. Now, we are going to use the state chart notation to represent the same system. This figure shows a state chart representation of the character display system which we have described earlier. Here, as you can see, there are three superstates: color, font size and character. So, color superstate or font size superstate or character superstate contains many basic states. Here we have mentioned that all the superstates combine both default state mechanism and the history mechanism. So, these two mechanisms are present in all the superstates. Now, one thing may be noted here that in font size superstate or character superstate, we have used some state transition networks with dotted lines. This is not part of the convention. So, typically this is not used in state chart notation. Here we have used it to simplify the depiction of a large chain of transitions for font size as well as the character. Since we have used the dotted line, it also indirectly indicates that the things are still not manageable, we can still go for improvement. So, possibly we may go for some further hierarchy in this case. So, how the hierarchy is taken care of? By defining superstates and defining connections between those superstates. And within each superstate, like before, we have these sub dialogues modeled using STNs, with the added advantage that this time we have specified the history mechanism and default state mechanism. So, now we know if one superstate is entered, say for example character, then where it should start. So, as per the default mechanism, so the state A should start whenever the character superstate is entered. As I said, since we have used dotted lines, that means we are still unable to show the entire system within a single page. So, there is possibly scope for more simplification by adding additional levels of hierarchy or additional levels of superstates. That is one advantage of using state chart, that is it allows us to represent hierarchy, but at the same time it allows us to specify the entry exit points in the hierarchy, which is not possible with hierarchical STNs. There is another advantage. Many interactive systems are actually concurrent in nature. The way they behave can be termed as concurrent behavior. What we mean by that? In the example system, we assume that the states are changed one after another, which was ensured by sequential nature of the interaction. So, we perform the interaction one after another to change the display state. Let us now consider a different design. Let us modify the design slightly. Suppose we are dispensing with the left right arrow key. So, what we are left with is only the up down arrow key. Now, this arrow key we are using to change both font size and character. How that is possible? Let us see. If we press the up key, then what happens is that the font size change to the next higher level, that is 14 becomes 16, and at the same time simultaneously the letter also changes to the next letter in the alphabet, that is A becomes B, and the down key does exactly the opposite of this. So, we can of course add certain constraints like the up key or the down key does not work at the boundaries. So, when we have reached the maximum font size or the last letter of the alphabet, the up key will not work. Similarly, the down key should not work when we have reached the minimum font size or the first letter of the alphabet. So, what is the difference between this design and the previous design? Remember that in the previous design, we can actually change font size and letter one after another by using different keys, but here that is not the case. Here both are changing together. Now, the earlier hierarchical STN model of our system or the state transition networks or the state chart model, none of these models of our system actually capture this concurrent behavior, and we need to modify the language actually to specify this concurrent behavior. Whatever we have learned so far about state chart is not sufficient to help us resolve this issue. However, it may be noted that state chart notation supports concurrency, and that is achieved with the idea of the AND superstates, and we need this notation to specify concurrency in our proposed model of the system. So, first let us try to understand what is this AND superstate. The AND relationship between superstates indicates that whenever the superstate is entered, all the substates are activated together according to the corresponding default state mechanism, and the states remain active as long as the superstate is active. The figure illustrates the idea. Now, S is a superstate, it has two substates T1 and T3. Each of these can have a subdialog models as shown here. Now, whenever S is entered, both T1 and T3 are active simultaneously. Now, what I mean by the term active? That means whenever they are entered, the basic state that is indicated by the default mechanism becomes active together. So, whenever S is entered, B1 and B3 get active together, because the default mechanism indicates so. So, in case of T1, the default mechanism says B1 should be the first state or default state. In case of T3, it states that B3 should be the default state. So, whenever S is entered, both these default states get active together, and the dotted line that separates the two substates T1 and T3 indicates AND relationship. So, with this notation we can represent concurrent behavior. Here T1 and T3 are concurrently active. Now, with this notion of concurrency, we can try to represent the character display system in terms of state chart notation. It will look something like this. Here now we have these two substates, the subdialog for font size and subdialog for character. They are now connected by the AND superstate notation. So, this font size and character is the superstate, and it is an AND superstate where the substates are font size and character. They are active simultaneously. Then the other superstate is color, and this AND superstate and the color superstate are connected with left right arrow key press and space key. So, it is, as you can see, it is in a much simpler form than the earlier one where concurrency was not taken into consideration. And as before, the subdialogues can be represented with STNs. However, there is some change. Now, actually, to traverse between the substates in these subdialogues, we no longer need the up down arrow key, or we no longer need the one set of arrow keys. So, that should be taken into account while modeling the subdialog for these substates font size and character. So, that is all about the basic idea how we can use a formal notation to model an interactive system. So, here we have shown how to use state charts, hierarchical STN and state transition networks to model interactive systems. So, first we started with state transition networks, and we have found that it is not suitable to model complex large practical systems. So, then we learned about hierarchical state transition networks, where we divide the problem into sub problems and create a hierarchy of sub problems to solve the overall problem. Now, there is some elements of ambiguity in this hierarchical state chart, and also it does not support concurrency. In order to handle those things while retaining the benefit of hierarchical representation, we learned about state chart notations. and we have seen how we can use it to represent complex systems, both supporting sequential behavior as well as concurrent behavior. The question is, so that is how we actually represent it. Now, what is next? Is it only to draw it on a paper that we learn these models, these formalisms? That is not necessarily, that is actually not the purpose. So, when we say we want to formally represent a system, definitely our objective is to be able to encode it in some language, so that it can be processed by computer. In other words, we can create a software out of it. So, there are tools to do that. In fact, state chart notation is a very common formalism used in software property verification, and accordingly there are many tools available for model specification or model implementation. That means translating the graphical representation to a code form, program form. Then there are tools available to specify system properties. So, state chart does not specify any property. State chart is a representation of the system, and we can actually verify this model, the state chart model, to check for presence or absence of system properties. So, what we need is to specify those properties as well, and together the specification of the model and the properties can be used for verification. So, there are tools available to do all these things, to specify the state chart model, to specify properties and to verify those properties. However, we will not go into the details of those are not in the scope of this lecture, but if you are interested, you can check the reference that will be mentioned at the end of this lecture. So, whatever we have discussed today are taken from this book. So, you can refer to chapter 8, section 8.4. Along with that, you can refer to other sections if you are interested to learn about how to use the specification, how to use the models, what are the tools available. You can get some introductory idea on these basic concepts. That is all for today. Thank you and goodbye.